variable force problems now where the force changes. This means the mass of the object changes as it moves. So most of the examples we have, it'll be like we're trying to move something a container that is leaking. So in that case, as it leaks over time, it would weigh less or have less mass. So it would probably use less force to move it because it would weigh less, and that means that as we go on, the amount of work done per unit would differ, but we'll probably find the total work as well. But basically what we mean here is that since the force is changing, we'll be writing it as a function of x as far as the distance here, which you've seen before, but now we have a varying force, not a constant force. So we have this example. It says a bag of sand weighs 144 pounds. So when it says pounds, that's automatically a force, okay? And it says it's lifted at a constant rate. So maybe it's on a pulley and we're pulling a rope to pull it up, but it's being lifted. It says the bag has a hole in it and leaks at a constant rate such that the bag is half gone by the time it reaches, and that should be 18 feet high. So it starts off weighing 144 pounds, and by the time we get it 18 feet high, half of it's gone, so it will be 72 pounds. And it says how much work is done to lift the bag to the height of 18 feet. So in that scenario, we're talking about trying to find the work. So we would have the displacement from 0 being on the ground, whatever, up to 18 feet. And we're going to have a force function that we will integrate. So that's how we're going to find the work. Okay? But we don't know our force function. So what do we know? We know that it starts off being 144 pounds and it's leaking at a constant rate. So that means we're going to subtract off some of the weight, and that weight would be some constant times however far it's moved. So if we knew at what rate it was leaking out here, the K, we'd just multiply how far we moved it, and that would tell us how much has leaked out. And if we take that from 144, that would tell us how much is left. So what they did tell us is that we're going to have 72 pounds, or half of it, left after it's 18 feet high. So 72 equals 144 minus K times 18. So 18 feet times some constant will give us how much sand has fallen out. Take that away from the 144, we'll have 32 left. So let's just kind of work through this. Solve for K, so negative 72 equals negative 18K. So in the end, K would be 4. So this force function for the variable force will be 144 minus 4K. So we'll come over here and we'll say from 0 to 18, from the ground, raising it 18 feet high, 144 minus 4K dx. So remember that the pounds is a force in itself, so we don't have to worry about the acceleration because it's already included in. But now we will integrate. So we'll have 144x minus 2x squared from 0 to 18. And we're going to let x equal 18. So 144 times 18 minus 2 times 18 squared. Plugging the 0 won't give us anything. Just need to make sure that happens though. So 144 times 18. And then we're going to subtract off 2 times 18 squared. And I get 1,944. And we're talking about work, and work is generally given in two different units. It's given in joules if we're talking about mass with kilograms and newtons for force, but we were given the force in pounds and we were given the distance or the movement in feet, so this will be in foot-pounds. Okay? So there's that example. Let's move on to another one. Okay, this is an example that's actually worked out in the book. It's example 4. it says a 5 kilogram water bucket. Okay, now that is mass. Okay, kilograms means mass, so that's not a force yet. A 5 kilogram water bucket is lifted from the ground by pulling a rope at a constant speed. So the bucket is going to move up at a constant speed. The rope weighs 0.08 kilograms per meter. So that means every meter of rope weighs 0.08 kilograms, which is also a mass in itself. How much work is done to raise the bucket 20 meters? So we need a force function to start off with. So with the force here, remember that's mass times acceleration. F equals ma. So let's see here. We're going to write that function. The mass was 5 kilograms, okay, and that's for the bucket. But then we're going to add to that something that's changing. We're going to add to the weight of the rope. So we're having to lift that rope as we go. And the rope weighs has a mass of 0.8 kilograms per meter. So 0.8 kilograms, but we need to take that into account as far as meters, because as we lift the bucket, there's less and less rope that we're trying to lift. Okay, so as we pull the rope down, we start with 20 meters of rope, which weighs a certain amount, has a certain amount of force to move, but then as we keep pulling it, there's less and less rope to move. So we need to include that varying weight or that varying force mass on the rope. So we know it's 0.08 kilograms per meter, and we start off with 20 meters, but we're subtracting off 1 meter for every unit. Okay, so as we increase x here, we'll decrease the amount of rope. Okay, so as we pull at a certain distance, the amount of rope decreases here, the 20 minus x. So when we multiply that times the mass, there will be less rope there. So the bucket isn't changing in this position, 5 kilograms of water staying there, but the amount of rope is changing. Now that is all mass. Okay, that is all mass. And we've got to take that times an acceleration, which is 9.8 meters per second squared. So let's just kind of clean that up so that we have a force function. We can do this many different ways, but let's kind of push it through, because once we get it, it'll be easy to integrate. So I'll take this and make it 5 times 9.8 is 49, and then plus 0.08 times 20 times 9.8 looks like 15.68, and then we'll have minus 0.08 times 9.8, and I hope I'm getting the right numbers here, but that'll be in terms of x, so 0.784x. So let's just clean that up a little bit more. So 49 plus 15.68 gives me 64.68 minus 0.784x. So keep in mind what this is. This is the force to raise the bucket and the rope, but the amount of rope left to move is decreasing as we continue on. So we're taking, as x increases, we're taking more and more mass away from this, so there's less force required. So let's set up our integral. It'll be from 0 to 20. This is for our work. Times our force, 64.68 minus 0.784x, and we're going to integrate that in terms of dx. So let's see here. That'll be 64.68x, and then we'll have minus, and we need to take the 0.784 and divide it by 2. So minus 0.392x squared from 0 to 20. And we know that when we let x equals 0, that's going to be 0. So let's just plug in our 20. So when we plug in our 20, it's 20 times 64.68, which is 1293.6, and then we're going to subtract off the other part. 20 squared times 0.392, so it'll be minus 156.8. So we'll subtract those two, and I get 1136.8. Now we're talking about work, and this was in terms of kilograms and meters. So when we got over here, we had mass times acceleration. So this thing, once we calculated the force, was in newtons. So newtons times meters, this will give us joules. Okay, so 1,136.8 joules. All right.